All right, now that we know electromagnetic waves exist, we are going to shift gears a little bit, and we are going to talk about light not as a wave, but as a ray, and we're going to talk about the ray model. So just a brief review from the section on electromagnetic waves, we determined that in vacuum, the speed of light is 3 times 10 to the 8 meters per second. And it turns out that light travels at lower speeds in media that is not the vacuum, is not empty space. And so speeds in these media are less than c, and the way that we characterize media is with something known as the index of refraction, which is just the ratio of the speed of light in vacuum to the speed of light in the given medium. And so that index of refraction is denoted with the letter n. So with our ray model, the ray model is as simple, really, as a model as you can imagine. The ray model is that light travels in a straight line until it doesn't. And a reason that light would alter the straight line motion is that there's an interaction with matter. And so the ray model is a great model for light when light is interacting with materials or matter that's significantly larger than the wavelength of light itself. And so light travels in a straight line. Rays originate from sources. Rays can be reflected or refracted at a boundary. We'll talk about reflection and refraction in a minute, but that's sort of highlighted by this figure over here. We've got rays traveling from left to right, and then at this boundary between material 1 and 2, you can get your rays to reflect. That would be to bounce back and stay in material 1. You could get your rays to refract, that is pass into material 2, but change direction. And then there's also some other phenomena, scattering and absorption, that we're not really going to get into. We're going to focus on reflection and refraction. So the basic approach that we're going to take when we're dealing with rays, and particularly next chapter when we talk about image formation, is we're going to be using ray diagrams. So ray diagrams are kind of highlighted over here. You can take any location on an object and treat that location as a point source. And so point sources are just regions that are generating light rays, and those light rays diverge from that point, so travel from that point in any/all directions. So we're going to be moving into next chapter talking about how those diverging rays, right, those rays that are spreading apart, how things like your eyeball, the lens in your eye, can alter the path of those diverging rays, and those rays can be brought into focus. And so before we do that, we need to introduce reflection and refraction, but that's kind of where we're headed. Right? How do you actually get to images formed? And the idea is that these rays that should be diverging, right, from the point source, if you can alter the path of these rays, then you can get those rays to converge at a location, and that's where you'll get an image to form. So treat your object as a source, even if the rays originate elsewhere. So like for this tree, certainly the tree that you see outside, those light rays are not being emitted by the tree itself. Those light rays are being reflected by the tree, those light rays originating from the sun or from the sky, which is light that's been scattered from the sun. And so the requirement, though, for you as a person to see an image of an object is the rays that are coming from that object need to somehow enter your eye, right? And so that's the whole goal here is to try to figure out ways in which rays can be manipulated, and the direction of the rays can be manipulated so that images can form, the rays can meet at a specific location. So we have two options when a ray is traveling through a medium and reaches a boundary. we can either have that ray reflect, and so in that scenario, the ray is going to stay in the original medium, or we can have the ray refract, that is, to enter in the new medium, and often when that happens, the ray changes direction. Just a side note here, at most boundaries, what happens when light reaches one of these media interfaces is that some of the rays pass through the medium into medium 2, and some of the rays are reflected. And so depending on the materials, depending on the properties, you may get most of the rays to transmit through and refract into the new medium, or you may get most of the rays to reflect. And so we're going to focus right now just on the idea of reflection. And to characterize reflection, we have the law of reflection. And the law of reflection is really the most straightforward law you can imagine. The law of reflection is that the incident angle of the ray that meets the surface, a reflected ray will be the outcome of that interaction, and the reflected ray and the incident ray angle will be exactly the same. And so when we're dealing with ray optics, we always measure our angles from this normal line. And again, it's called normal, hopefully for an obvious reason, because that angle between the surface and the normal line is 90 degrees. And so that's the law of reflection. Any ray incident on a surface will reflect at the exact same angle that it was incident. Now, an interesting thing happens for most surfaces. Most surfaces are rough. And so that means when you have rays, in this case, notice how I've got a whole bunch of parallel rays. They're all traveling the same direction. And when those rays go to hit the surface, notice that the surface is rough. And so the normal to the surface is not the same direction at all the different locations on the surface. Since the surface is rough, those rays get scattered essentially randomly. And so what we need if we want to consistently form images using reflection is we need a polished or smooth surface, which I suppose probably seems obvious to you. So we need a mirror if we want to be able to have consistent usage of the law of reflection, right? In this picture up here, the law of reflection is holding. It's just that the surface is inconsistent, and so that you can't really predict which direction any given ray is going to reflect. Whereas if the surface is completely smooth, then all of the reflected rays would be at that same incident angle. And what about the other possibility, that the rays pass into the new medium? Well, that's described by the law of refraction, or what's often referred to as Snell's law. And so I've got this picture from the book. I've got somebody looking into a fish tank, and by looking into the fish tank, the person is able to see multiple images of the fish that's inside. Even though there's only one fish, you can see the fish itself is actually in the center, and the rays that are leaving the fish tank bend and make their way to the observer's eye, giving rise to multiple images of the fish. Right, so your eye and your brain are incredibly advanced and useful instruments, but very simplistic in the sense that all that matters for your eye and for your brain is that the rays enter, and then your brain does the work of tracing back those rays in straight lines. And so ultimately what you see is multiple images of an object, even though there's only one object, because all your eyes and your brain are doing are tracing the rays that enter your eye back, and that's the resulting interpretation. And so light rays enter new medium, can change direction. Why? Well, it's because light travels at different speeds in different media. And again, this index of refraction is the way that we characterize or quantify that speed or in a given medium, right? Index of refraction is the ratio of the speed of light in vacuum to speed of light in the given medium. So how do we quantify how much light bends as it passes from one medium into the other? This is Snell's law, or the law of refraction. And so I've got this this image here of a light ray passing from medium 1 into medium 2. And so you want to know how much the light bends, what's the angle 2 there. There's a specific relationship between the index of refraction in each medium and the incident angles, or the refracted angles in the media. And so this is known as Snell's law. N1 sine theta 1 equals N2 sine theta 2. Remember, both of those angles are measured from the normal. So if you look at the picture here, I've got a surface and then my normal to that surface, right, perpendicular to that. And so theta 1 is going to be measured from the normal, theta 2 will be measured from the normal. Now, since the index of refraction is connected to the speed of light in the given medium, you essentially have a few ways of interpreting what's going on here. And so I've got this additional figure down here that I've made. So let's see what happens. We've got an incident ray, and so we could call this theta 1. And so as the ray passes into medium 2, there's essentially three possibilities. The first possibility is that the ray continues on at the exact same angle and doesn't change direction at all. And that's possible if N1 and N2 are the same value. Now, remember, the index of refraction is connected to the speed of light in that medium. And so that would mean if the light passes straight through without changing direction, that means that the speed of light in both of those medium is exactly the same. All right, so that's our first option, or one of our three options. The next thing that could happen is you've got your light ray coming in, and the light could bend away from the normal. Notice how this angle, theta 2, is larger than theta 1. Right, so the light ray has changed direction. The angle now is larger, so it's bent. The light ray has bent away from the normal, we would say. And what that means is that the index of refraction in 1 is larger than the index of refraction in 2. Now again, index of refraction is connected to speed, so what that really means, the physical interpretation, is that light travels faster in the second medium. V1 is smaller than V2 for the example where the ray bends away from the normal. Now, the last possibility is that the ray comes in and bends towards the normal. This angle here now, theta 2, is smaller than theta 1. When that happens, that immediately means that N1 is smaller than N2. And again, since the index is connected to the speed, it means that the speed of light in medium 1 is larger than the speed of light in medium 2. You can see that written down there. So if your ray of light passes into the new medium and the angle doesn't change, as long as the angle isn't 0 degrees, if the angle doesn't change, then that means the index of refraction in both media is exactly the same. So the speed of light in both media is the same. If the light ray bends away from the normal, that means the light ray will be traveling faster in the new medium. If the light ray bends towards the normal, that means the light ray will be traveling slower in medium 2. So you can think of stays the same speed, speeds up, slows down. And those are your options when you're interpreting what exactly is happening when you use Snell's law.